In this work, we introduce a unified reinforcement learning and optimal control-based approach for dynamic, terrain-aware quadrupedal locomotion. We use the animal B quadruped to design, train and evaluate our control framework, and further transfer it to animal C. We are able to do this transfer without retraining any of our RL policies, despite the fact that animal C is different compared to animal B in terms of mass and size. As part of our framework, we introduce 3 RL policies. A first-step planning policy, which, given terrain and robot state information, generates desired feed positions and forwards it to a whole-body motion controller. A domain adaptive tracking policy, which generates corrective feed-forward torques in order to aid whole-body motion tracking. And finally, an emergency recovery controller, which generates low-level joint position commands for quick responses to external perturbations. We use the elevation map local to the robot's base frame as a form of extraceptive feedback. However, instead of including it directly in the observation space of each of the RL policies, we train a denoising convolutional autoencoder so as to represent the elevation map in the form of a reduced dimensional embedded vector. This embedded representation of the elevation map, along with the robot states, becomes the observation space for each of our RL policies. Furthermore, since we use a physics simulator to train these policies, it becomes necessary to accurately model the dynamics of the system, making it easier to perform a sim-to-real transfer. In this regard, we introduce an actuator network as an approximation of the complex actuation dynamics of the physical system to generate an effective joint torque for joint position, velocity, and feed-forward torque commands. Moreover, in order to obtain robust RL policies, we perform training over a large set of terrains. After training, we evaluate each of our RL policies on a wide range of tasks and present that our method is able to surpass the baseline by a large margin on complex terrains such as those consisting of bricks. We also show that our control framework is able to closely track the user-generated reference space velocity commands even on uneven terrain. Depending upon the complexity of the terrain, our control framework enables the user to select from different locomotion gates, also enabling online transitions as shown here, where the robot switches from trot to crawl gait. Despite having been trained using the RISEM simulator, we show that we are able to transfer our RL policies onto the real robot. In this work, we demonstrate that our control framework enables the user or a high-level goal planner to command the robot so as to track the desired reference base velocity on uneven terrain. We further demonstrate the increased robustness offered by our method on 2 different quadrupedal systems, and conclude that our approach results in dynamic legged locomotion behavior on uneven terrain.